using for in a specific context. So this level 2 guest, this nested guest, if we want to run, it should also has a corresponding VMCS. That VMCS is a virtual VMCS presented by the VMM. And this, the level 1 guest sees this VMCS as a controlling VMCS of the level 2 guest, but actually it's virtual. It's something presented by the base VMM. So the base VMM, in fact, also has a corresponding shadow VMCS. This shadow VMCS is not a duplicate of the virtual VMCS, but has some translations and but corresponds to the virtual VMCS. The shadow VMCS is actually the VMCS that is finally loaded to the real one, to the real hardware VMCS. So this shows a typical situation of only one level 2 guest. If there is more than one level 2 guest, it's similar. It's just the same way. And you can see at the bottom line, there are now 3 VMCS. The VMCS 1 for controlling the level 1 guest, and 2 other shadow VMCS to control the nested guests. And these VMCSs are in a single vCPU context. The general idea of nested virtualization is to treat these VMCS all as the guest of the base VMM, as the VMCS of them. And we'll have an internal VMCS switch between a single vCPU context. And I will address that later. So this is a closer look from timing aspect of the execution of nested virtualization. The top level is a scenario of a native execution. You see it has only one line, one block to illustrate the execution of a single OS that fills all the execution. And in a normal virtualization scenario, we have a VMM and a guest, and there is a controlling VMCS that is always there for this guest. You can see the VM entry and VM exit. As we mentioned before, it's like this transition goes over and over and driving the execution forward. Now, for the nested virtualization, you can see from the very left, it's now the level 1 which is running. And when it wants to do a VM entry, either by VM launch or VM resume, instead of getting directly into level 2, because this is not directly because there's no such hardware support. The level 1 is already in the VMX non-root mode, and it can only cause a VM exit to the base level. And then VM exit to the VMM, the level 0. Level 0 can intercept this VM entry call, and when it sees this VM entry, it tries to do a switch to the level 2 shadow VMCS, and then re-enter the guest mode, and it goes to the level 2 guest. And this realizes a virtual VM entry. Similarly, when the level 2 guest has some sort of events, and it has to exit. It exits directly to the level 0. And here, level 0 will have a kind of algorithm to see whether this VM access should be handled by the level 0 itself or forwarded to the level 2. If it decides to forward it to level 2, it also changed the control of VMCS to the level 1 the VMCS of nest VMM and VM entry. And this realizes a virtual VM access, as this figure shows. So this is a timing wheel of the execution. We can also have a block wheel on it. Simply, these execution flow transitions, it can be simply considered as a lightweight guest switch. You can see here is nested VMM and nested guests in the level 1 guest pointer wheel. This dotted black arrow is the VM entry and the VM exit. We can simply consider these nested guests as the guest. These both are the guest of level 0 or the VMM. So first is the VM entry. When the virtual VM entry happens, the execution goes to the VMM, and the VMM, when VMM find it, it will do a transition to the level 2 SVMCS, and then enter into level 2. And particular the jumping point of this VM entry is the guest RIP register in virtual VMCS. That is the RIP target running point in the nested virtualization, in the nested VMM. A similar thing happens in the virtual VM exit. One of the big differences when the VM exit of L2 happens, at very first it cannot be known whether it's a virtual VM exit or level 0 should handle it directly. So there's like a policy, like a judgment, and if it's a virtual VM asset, the VMM will also do a guest switch and turn back to the level 1. So when will it be not be a virtual VM asset, but return directly to the level 2 guest? A notable example is page fault. The page fault can, very like the ordinary memory virtualization system, can be of different origins. It may be a guest page fault or a shadow page fault. If the page fault is a level 0 shadow page fault, then the level 0 VMM will do it itself and then return directly to the level 2 guest. So there are also other VM exits drawn here. The right black arrow is what we refer to. We just referred to, and the two arrows in the left are the ordinary level 1 VM exits. These generally also all happens in the same with-view context. That is kind of different from traditional ZAN scheduling. That is the CPU virtualization. The memory virtualization. The memory should have no big handling if we are using the shadow memory, since the shadow memory is purely software. But the performance is kind of bad because shadow memory has a lot of page faults, and these page faults are VM exits, reflects to VM exits. In the nested virtualization, these are virtual VM exits. But virtual VM exits is kind of very, very slow because it goes to the base level of VMM, and it has quite a long time. Nested EPT will be very helpful here, since the NestAPT greatly reduced number of virtual VM access. The NestAPT's